Catalyst video is all about, you guessed it, buffers. This is part one of the two-part series on buffers. What is a buffer, you might ask? Well, a buffer is a solution that resists a change in pH. If you can see here, these are three different buffers that are set up around different pH ranges, one around 4, one around 6, and one around 9. And if we took this buffer at around 4 and we added acid or base to that, it would actually resist the change in pH and stay very close to that pH value of 4. Why is that important? Well, if you think about a biological system like your own body, you have buffers in your body that maintain the pH so that if acid is generated inside your body, it will not change the pH of your blood or inside the cell because pH changes can be damaging to tissues. There are a couple ways to make a buffer. We're primarily in this video going to focus on this way, which is number one, which is by taking a weak acid and its conjugate base, or a weak base and its conjugate acid, the salt of its conjugate acid. And by salt, we mean ionic compound. Like if you had citric acid, if you had acetic acid, that would be acetic acid would be the weak acid, and sodium acetate would be an example of the salt of its conjugate base. You can also add strong acid and partially neutralize that with a weak base. That would be a buffer system, or strong base and partially neutralize that with a weak acid. We'll deal with these calculations in buffers part 2 after we do titrations. So how does a buffer work, or how do buffers work in general? Well, we're going to consider a buffered system with, let's call 0.10 molar acetic acid and 0.10 molar sodium acetate. And sodium acetate would be NaC2H3O2. But when you dissolve that, it's going to produce Na plus the acetate down here. And so that's all we're really concerned about. So we have a buffered system here. And we know that Ka for this equation is going to equal the concentration of H plus times the concentration of C2H3O2 minus, and over the concentration of acetic acid. All right, so Ka is a constant. Here's the value for Ka. That means if it's constant, that means that this ratio needs to stay the same. So let's say I add H plus to this system at equilibrium. Well, what does Le Chatelier's principle say is going to happen? If I add H plus, it says that's the stress. The system is going to shift to reduce the stress. It's going to increase the reverse reaction to try to get rid of the H plus. Well, since it's a buffered system and I have some acetate here, that acetate can combine with the added H plus to speed up the reverse reaction to make more acetic acid. And that counteracts the fact that I added acid. So that's how a buffer works. And if I add a base, the base would remove the H plus, right, which would decrease this value. And so the system would increase the forward reaction to make more of the H plus and therefore restore the pH value. So buffers are really pretty neat in that they take advantage of equilibrium systems to make sure that your pH is buffered. Now, they don't have an infinite lifespan. A buffer will break down if you add enough acid or base to it, but they do a good job of resisting pH changes when you add acid or base. Let's look at a problem. Lactic acid and sodium lactate buffer. So lactic acid is HC3H5O3. Now, here's our equilibrium system. And again, all aqueous. And so initially what we have here is 0.12 molar, 0, and this is not 0 like it would be in our weak acid problems that we've done. It's 0.10 molar. And we get that because it's given to us as sodium lactate. The sodium lactate would dissolve and this would be lactate. So our change, minus X, plus X, plus X. You might say, whoa, wait a minute, how do I know that? Well, folks, this Q value would be 0. And again, Q is an equilibrium concept. You have to go back to that, but you'd have 0 times that divided by that, which would be 0. Q can't be 0. Well, it could be, but that means that the reaction needs to proceed in the forward direction. And then our equilibrium condition would be 0.12 minus X, and 0.10 plus x. So we plug them into our Ka equation. X and we realize now that x is going to be negligible. You might say, what do you mean negligible? Well, x, since k is so small, this dissociation isn't going to be very great. So this x value isn't going to impact 0.1 or 0.12. Essentially, if we add x to 0.1, it will still be 0.1. If we subtract x from 0.12, it will essentially still be 0.12. So we're saving us some math work, and then we're going to solve for x, which would equal the Ka, which is 1.4. Let's clear this out. This is a new toy here, and I can't even work it. So our Ka is 1.4 e to the negative fourth times 0.12 divided by 0.1, and I get 1.68 e to the negative fourth for my x value, and then to get the pH, that's my x value, so the pH is just negative log second answer, and I end up with a pH equal to 3.77. That's pretty cool. All right, I figured out my pH for the buffer. But enter our best friend, Mr. David Hasselhoff, who has absolutely nothing to do with this, but my friends, people have told me that Henderson Hasselbalch sounds like David Hasselhoff. Henderson Hasselbalch sounds like David Hasselhoff if you say it very quickly, and so therefore it is the Henderson Hasselbalch equation. We like to think of it as the David Hasselhoff equation. Whatever you call it, I am fine with it. This tells us that the pH of a buffer is equal to the pKa plus the log of the concentration of base over acid. So it allows us to do this problem in a much simpler way. We take the pH is equal to the pKa, which is the negative log of 1.4 times 10 to the negative fourth, plus the log of the base over the acid. Well, the base was 0.1, the acid, because that's the conjugate base, and the acid was 0.12. So let's take a look. Pull up our solver, and the solver tells us here that when we go negative log of 1.4 e to the negative fourth plus the log of 0.1 divided by 0.12, we get our pH, 3.77, which is exactly what we got in the previous problem. Don't believe me? Well, they are the same problem, but just two different ways of going about it. So that's the basics of buffer calculation, and those are the really easy problems. Buffers part 2 is going to take us into more challenging concepts, and I'm going to introduce that with this problem right here. Let's say, in this case, we're going to have a buffer, which is a straightforward calculation. We're going to calculate the pH, and then we're going to add some acid or base to it. In this case, we're going to add base, which is going to introduce a new concept. So in this case, we have an acetic acid buffer, and it's 0.3 molar with respect to the acetic acid, and it's 0.3 molar with respect to the sodium acetate. They're both in 1 liter of solution, so the molarity is going to be the same as the number of moles. So we'll jump right in with Henderson Hasselbalch. pH equals negative log of the Ka. Sorry, that would be the negative log of the Ka, because that is pKa, plus the log of the base over concentration of acid. Think Ba. Base over acid, negative log of the Ba. All right, now you need to know the Ka here. So the Ka, I looked it up, and it's 1.8 times the 10 to the negative fifth. That's the Ka value for this equation. So we pull up our handy-dandy solver here, and we say that we have pH. Let's move this, actually. It's kind of in the wrong spot. It's 1.8 times the negative fifth. That's what we need. So what we're going to do here is say that we have the negative log of the Ka, which is 1.8 e to the negative fifth, plus the log of, in this case, the log of the base, which is 0.3 moles, 0.3 molar, 0.3 divided by 0.3. Well, that's simple because that's just 1. The log, or that's 0 because the log of 1 is 0. So the pH is 4.74. All right. So that was easy. That's using Henderson-Hasselbalch, so we don't have to do the ice chart. This part B is a little bit more challenging because it asks us basically to calculate the pH after we've added some sodium hydroxide. So when we do these, we have to figure out the reaction. So we have an acid here, and we have a base. Acids will react with bases. Bases will react with acids. If we were adding bases, it wouldn't. You have to figure out basically the acid reacts with the base. So I want to write that reaction down. It's going to be CH3 COOH plus OH minus, because I don't worry about the sodium, just the hydroxide because it's a strong base. And that's going to produce H2O plus the acetate, CH3COO minus. All right, we're going to do a new chart here called a BCA chart, which stands for before, change, and after. This is really the stoichiometry of the reaction. We have to do the stoichiometry calculation first, and then we can calculate the pH. So we started off with 0.300 moles of this, and 0.300 moles of this, and 0. Now, so it's 5 milliliters, so 0.05, right? 0.005, sorry, liters times 4 moles per liter is 0.02. So we added 0.02 moles, right, of the OH minus. And if we think about this in terms of stoichiometry, well, if that's the case, this is our limiting reactant. So this would go down by 0.02 moles. This would go down by 0.02 moles. And this is going to go up by 0.02 moles. And then at equilibrium, this would be 0.320 moles. This would be 0 moles. And this would be 0.320 moles. Now, the interesting thing about that is now I can calculate the pH using the Henderson-Hasselbalch equation, because pH equals negative log of the Ka, which I have. That doesn't change. I haven't changed temperature. 1.8 times the negative fifth plus the log of Ba. So the log of the base over the log of the acid. Oops, this is not 0.320. Sorry, this is 0.280 moles. Excuse me about that. And then therefore, my pH in this case is going to equal, do this on my calculator, negative log of, let's make sure this is right. Yep. 1.8 e to the negative fifth plus the log of 0.32 divided by 2.8, 0.28, and I end up with a pH of 4.80. Now that's interesting. My pH, even though I added that much base, my pH hardly changed. So this is an interesting question here. It says, for comparison, calculate the pH of a solution made by adding that many milliliters of water, of base, of that concentration of base to pure water. Well, this is kind of cool. If I'm checking that out here, if I had pure water, all right, and I added the sodium hydroxide, which is 5 milliliters which is 0.005 liters, times 4.0 moles per 1 liter, I'd end up with 0.020 moles of hydroxide. All right? And that's in a solution that has a volume of 1 liter, so that would be the same as the molarity. So my pOH would be the negative log of 0.020, which in this case of 0.020 gives me a value of pOH equal to 1.699. Now, that's my pOH. My pH is 14 minus that, so my pH is 14 minus 1.699. And my pH equals 12.30. Now that's pretty interesting if you think about that. That in the buffered solution, the pH only changed by 0.06 of a pH unit. It went from 0.74 to 0.80. That same amount of base to pure water has a pH of about 7, would change it by about 5 pH units. So that shows you that buffered solutions do a fantastic job of resisting change in pH.